Welcome back. Let's discuss section 6.3, using the fundamental theorem to find definite integrals. In this section, we learn how to evaluate a definite integral exactly. Now, if function little f is continuous, we know it has an antiderivative big F. So we can use the fundamental theorem of calculus, which says if little f is continuous on the interval a, b, and big F of x is an antiderivative of little f. In other words, big F prime of x equals little f of x. Then the value of the definite integral from a to b of little f of x is big F of b minus big F of a. So as long as we can find an antiderivative, this gives us a pretty straightforward way of evaluating a definite integral. And the advantage here is we get an exact answer as opposed to the approximation we were getting earlier when we used a left or right sum. Let's look at an example. Use the fundamental theorem to evaluate the definite integral from 0 to 2 of 3t squared plus 4t plus 3 exactly. What we need to do is find an antiderivative of this function that's in the integrand. So we need to find an antiderivative of 3t squared plus 4t plus 3. And here's a possibility. 3 times t cubed over 3 plus 4 times t squared over 2 plus 3t. Notice I'm not adding the constant c, the constant of integration. We'll talk about that more in a moment. And then I use this notation here, vertical bar from 0 to 2, to indicate that we're going to evaluate the antiderivative at 2, so f of 2, and then subtract this thing evaluated at the lower limit 0, so minus f of 0. And when we do that, f of 2 looks like this, ends up being 22. F of 0 in this case ends up being 0, so we end up with 22 for the exact value of the definite integral. As I said, we don't necessarily need to add the plus c when we find our antiderivative. Had we done that, notice what happens when we evaluate f of 2, we add c. And when we evaluate f of 0, we add c, but we end up subtracting these things, and so the constant c cancels. So we really don't need to add it in the first place. So we'll stop there for now.